Hello students, Professor Gray here with some significant digits. So, what are significant digits or significant figures? Exactly the same thing. Well, let's take a look at these three rulers here. Now, they are slightly different, but we're going to measure the same object with all three different rulers and see what measurements we come up with. But first, let's take a look at these three numbers over here. So we have 3, 3.0, and 3.00. Now, in everyday real life, those numbers are exactly the same thing. If you buy 3 boxes of cereal, you're buying 3.0 boxes of cereal or 3.00 boxes of cereal. It's all the same thing. But in science, those numbers are different. Those numbers are telling us a little bit of information about the measuring device we use to measure those values. So if we are measuring object X with ruler 1, and ruler 1 only measures by every 10 centimeters, so we can see down here it's in centimeters, so it goes 0, 10, 20, 30 centimeters. And we put that up against object X. What we're going to have to do is we're going to have to make a guess. And we might look at that and say, okay, well, I'm guessing that object X is measuring about 3 centimeters. So this right here is our guess, or we can say it's our estimate. Let's make that a good A, estimate. Either way, this number right here is uncertain. It could be 2 centimeters or it could measure 4 centimeters, but our best guess is that it's 3 centimeters. Now this guess here, this is significant. That is significant information. It's telling us that the ruler is measuring every 10 centimeters, and that if we're reporting in the ones column, which is right here, this is a guess right here. So it's telling us about the precision of this instrument. Now, if we measure object X with ruler number 2, what we can see is that ruler number 2 has increments every 1 centimeter. So if we measure object X with ruler 2, what we can see is that object X is measuring 3 centimeters. It's not 2 centimeters and it's not 4 centimeters. So this 3 right here, that is certain. And then we are going to make a guess as to what the next value is. So maybe one person says, I think that's right on 3.0, and another person says, I think that's 3.1, and somebody else says that's 3.2. Now, all of those measurements are correct, and the reason is because this end value that's reported is a guess. It's an estimate. It's uncertain. So what we're saying when we report object X as measuring 3.0 centimeters is we're saying we're sure that it's 3. We're sure that it's not 2 and it's not 4 centimeters. We're all sure that it's measuring 3 centimeters. But then we have to report another value, which is our guess. And that one has wiggle room. So if you're measuring this with a partner, you might measure 3.0 and your partner might measure 3.1. And both of those are correct, as long as you're both getting your certain value the same, the 3. Okay, so say we want to measure object X with ruler number 3. Now, object X, it looks like it suddenly got bigger. but I had to draw it a little bit bigger there so we could see the tiny little increments there. So what we're measuring here is by tenths of a centimeter. So the big numbers, those are our centimeters, and the little tiny numbers, the little tiny increments, those are millimeters, or we can say we have 0.1, 0.2, 0.3, blah, blah, blah centimeters there. Okay, so object X, when we take a look at it, we can see that we're sure that object X is measuring 3 centimeters, and we're sure that it's not measuring 2 centimeters or 4 centimeters. So this right here, that's a certain value. We're sure that it's 3 and not 2 or not 4. And don't worry about how the millimeters aren't drawn over there. I had to draw this little thing by hand, so after 4 I just thought, okay, that's enough of tiny little marks. Okay, so then we can see that not only do we measure each centimeter, but we measure tenths of a centimeter. So we've got 3 and we've got 3.1 right there, and we've got 3.2 next to it. So we look at this and we say, okay, that looks like object X is measuring 3.0, and it's not yet to 3.1, and it surely isn't to 3.2, so we're also certain about this value here. We are sure it's not 3.1 or 3.2. We're sure it's 3.0 something. Okay, now when we're measuring this, like we did above, our last value needs to be a guess. And this really is weird to students, that you need to make a guess. But we do. And what we see is that for me, what I said is, I'm sure that it's 3 centimeters. I am sure that it's 3.0 centimeters. And I think that it's 3.00 centimeters. So this one right here would be my guess or my estimate. That would be uncertain. And my measuring device does not have a measuring increment right there. Now, if you look at this picture and you go, oh no, I think it's 3.01 or 3.02 because it looks like it's slightly past exactly 3.00, would you be correct if you reported this as 3.01 centimeters? Yes, because these two values are certain. So my measurement should match your measurement in those two spots, but on the end is where we have a little bit of wiggle room because that's where we have the guess. Okay, so these values are different in science because what they're telling you is how precise your instrument is. So it's telling you information about the precision of your instrument. So those are significant digits. So this value right here has 1 significant digit. So 1 sig fig here, 2 sig figs here, and 3 sig figs here. The guess is significant, but you don't make more guesses. We wouldn't put an extra 0 on the end here because this number right here is already a guess, so that doesn't make any sense there. All right, so let's look at some measuring devices so we can get more familiar with this. So we've got 2 scales here, or 2 balances, and what we'll notice in the balance or the scale on the left-hand side is that this is measuring by every 1 gram. So you can see 0, 1, 2, 3, all the way to 10. So it's measuring every 1 gram. We put the pistachio on this scale, and we can look at it and see, okay, it's definitely measuring 1 gram and it's not yet to 2 grams. So we are certain that it's at least 1 gram. Now, this scale does not measure by tenths of a gram, meaning 1.1, 1.2, 1.3, but we need to make that guess. We need to go all the way to a guess. So we're sure that it's 1 and not 2 yet, and it's not 0. And when we look at that, we go, okay, our best guess is that it's 1.2. But what if your partner looked at it and said, no, 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 I think that's 1.3 grams? Would that also be correct? Yes, because the spot all the way to the right in your measurement value is uncertain. That's your guess, okay? But both of them are significant, okay? Your certain values and your one uncertain value, those are significant. All right, so let's look at another measuring device for the same pistachio. So right here, we can see that our pistachio is definitely measuring 1 gram, and it's not measuring 0 point something grams, and it's not measuring 2 grams. So right here, that 1 is certain. We are certain that's 1 something. Now, this measuring device has more precision. So what we can see is that this one is measuring by tenths of a gram. And we can see that it is a little past 0.2 or 1.2, but it has not yet reached 1.3, and it's definitely not in the 1.1 zone. So the 1.2, that value of 2 there, is also certain. We're certain that this pistachio is not measuring 1.1 or 1.3 grams. It's 1.2 something. Now we have to make a guess. So this balance does not have markings in the hundredths, so the 2's in the tenths column and the 7 is in the hundredths. But remember, we need to make a guess where we don't have markings. So we look at that and we say, okay, it's in between 1.2 and 1.3 somewhere, and my best guess is that it's 1.27. So that 7 is uncertain. And then we don't put any more digits behind the 7 because that wouldn't make sense. So all of your certain digits and your one uncertain digit on the end are significant. Okay, they mean something. So rules for significant figures. So what if we have the measurement 765 centimeters? How many significant digits do we have there? Well, the rules for significant digits say that all non-zero numbers are significant. So say you weren't measuring anything, somebody just told you the length of object X is 765 centimeters. Well, you would look at that and you'd say rule number 2 says that all non-zero numbers are significant. There's 3 non-zero digits here, so you've got 3 significant figures there, or 3 significant digits. Now, zeros may or may not be significant. Zeros are kind of funny. So zeros are significant if they're between 2 non-zero digits. So say someone told you that object X is 707 centimeters long. That 0 is in between 2 non-zero digits, so this measurement here also has 3 significant digits. So the first 2 we would be certain about. So we're certain that object X is measuring 700 centimeters and not 600 centimeters or 800 centimeters. And we are sure that object X is measuring 700 and not 707 and not 717 or 727. So I'm saying we are certain that that's a 0 there and not a 1 or a 2. And then on the end here, we are uncertain. So we're not sure if object X is measuring 706 or 707 or 708 centimeters, but our best guess is that it's 707 centimeters. So that's how that works. The same with the 765 above. And B says if the zeros are at the end of a decimal number, so if they're all the way to the right of a decimal number, they're also called trailing zeros. And what that means is if we had a number like this 0 all the way to the right of our decimal number, of that trailing 0 there, that is significant. It gives us certain information. It tells us that we are certain that that 4 right there is a 4 and not a 3 or a 5, but this on the end is our guess. If we reported our measurement as 0.87734, that would be saying that the 4 was a guess and we were not certain about the 4 in this value. So that might be 0.87733 or 0.8734 or 0.8735, but our best guess is it's 0.87734. The 3, the 877 and the 3 in the bottom value are certain. Okay, so this one, if you throw a 0 on the end there, it's telling your reader that your measuring device is more precise than the one you use to measure this value right here. Okay, all right. So zeros are not significant if they are used as placeholders in large numbers without a decimal point. So if we have the number 800, that value has one significant figure. It's the 8. The zeros right there, those are placeholders because you cannot write 800 without writing those zeros there. If you did not write those placeholder zeros there, your number would be 8, and 8 is not the same as 800. So the 8 is the only significant digit, and when you only have one significant digit, it's your uncertain one. So if you're measuring this, you're not sure if it's 700, 800, or 900, but your best guess is that it's 800, okay? You could also write this as 8 times 10 to the third, and that would indicate that you only have one significant digit because rule number 6 says all numbers displayed in a number written in scientific notation are significant. And that should say all the numbers in the coefficient just to make it more clear. Okay, so we're using the zeros as placeholders for this large number here. And 5b says they are at the beginning of a decimal number. Okay, so say we have 0.0000324. These zeros up here are placeholders. If you took them away, you would have 0.324. 0.324 is a lot bigger than 0.000324. So this right here has 3 significant figures because the zeros in the front are placeholders. Now if we change this number to 0.000324, how many significant digits would we have then? we would have 4 significant digits, 4 significant figures. We put that 0 on the end there because we're saying that the measuring device we use to get this measurement is more precise than the measuring device we use to get this measurement. And now with the bottom measurement, we are certain about the 4. We're certain about the 4. Whereas in this measurement, the 4 is uncertain. Okay? So the 0 on the end there, that's the best guess. So the person making that measurement is guessing there's a 0 on the end there instead of a 1 or a 2. But maybe your partner measures it and your partner measures that right there instead of that right there, and that's just fine. Okay? So that's how that's working. So when they're placeholders, they're not significant. All right, let's do some problems. So let's identify the correct number of significant digits in the measurements below. And don't worry about if it's centimeters or milliliters or kilograms. Let's just look at the numbers. So number 1, 45. How many significant digits do we have there? What we have is 2 significant digits, so 2 sig figs there. What about with number 2? So number 2 is definitely different from number 1 on purpose. So we added an extra digit there on purpose. That one is 3 significant figures. So by saying 0.0, we're now saying that the 4 and the 5 are certain, and the 0 is our estimate, our guess. Whereas in just plain old 45, the 4 is certain, but the 5, oops, why did I write uncertain for 4? 4 is certain. And the 5 is uncertain. So in number 1, we're not sure if we've got 44, 45, or 46 milligrams, but we are sure that we have 40-something, and we don't have 30-something or 50-something. So the tens column is for sure, and the ones column is not for sure. Now with number 2, what we're saying is we are certain that we have 45. We do not have 44 or 46, and we are uncertain whether we have 45.0 grams or 45.1 grams or 45.2 grams, but our best guess is that it's 45.0. And remember the guess, the one guess on the end is significant. So 45.0 has 3 sig figs. What about number 3? That's 3 sig figs because all zeros are significant when they're in between 2 non-zero digits. How about number 4? Number 4 is 3 sig figs. The 0 between those 2 non-zero digits there is significant. Those are the rules. And the 0 on the end right here, that's a placeholder. So our uncertain digit is which one? The 4, the first 0, the 5, or the last 0? The 5 right there is uncertain. And the 4 and the 0, those are certain. And then the 0 on the end is just a placeholder. So we've got 3 significant digits here. Okay, so we're not sure if we have 4,040, 4,050, or 4,060, but 4,050 is our best guess. Okay, number 5. So we've purposely put a decimal point here. And that's saying that this 0 right here is significant. Okay, so it's saying that now we've got a better measuring device. And it's saying that we're certain about the 4, the 0, and the 5, but we're just uncertain about that 0 on the end. So we're sure that we have 4,050 something. So 4,050 or 4,051 or 4,052. But our best guess is that it's 4,050. So that one right there, number 5, has 4 significant figures. And we made that 0 on the end there significant by putting the decimal point there. That's how we do that. We could also write number 4 as 4.05 times 10 to the 3, which will tell us we've got 3 significant digits there. And we would write 5 how? We would write it 4.050 times 10 to the 3rd. And this right here, the coefficient with 4 digits, is telling us that we've got 4 significant figures in our standard form, because rule number 6 says all numbers displayed in a number written in scientific notation are significant. That's just the rule. Okay, how about number 6? So these ones right here are definitely significant, right? Because we know all non-zero digits are significant, and any of our zeros that are between non-zero digits are significant. But what about these up front? Those are placeholders. You can't write 0.000405 without those zeros, or you'd have 0.405, which is a lot bigger than 0.000405. So this one right here has 3 significant figures. What about number 7? So in the front of the number, we've already determined that those ones right there are just placeholders. So those are not significant. We know that this number right here is significant because it's between 2 non-zero digits. But what about these 2 on the end? Yes, they are. Number 7 is purposely written different from number 6 because those 2 zeros all the way to the right give us information. They tell us that our measuring device that gave us the measurement, number 7, is a lot more precise than the measuring device that gave us the measurement in number 6. And what it's saying is that we have 5 significant figures here. Okay, so this rule back here that says zeros are significant if they are at the end of a decimal number, meaning all the way to the right. They're also called trailing zeros. So like we said, this 0 on the end there, that is significant. Okay, number 8. So number 8 is a weird one. So the decimal here is telling us that for sure those digits are significant, those zeros are significant. We put that decimal there on purpose, okay? So if we wanted to just report it as 900, we could write that, but just 900, that would have how many sig figs? That would only have 1. That 9 there, and the 9 would be the guess. But if we put a decimal on the end, right there, that's telling us that the 0 to the left of it is significant. And if you've got a 0 in between 2 significant digits, then it has to be significant also. So this would be 3 significant digits, so 3 sig figs. Now we purposely put another 2 zeros out there. And that means that we've got 2 more significant digits. It's telling you that that measuring device is reading all the way out there. So that right there is the guess on the end, but remember your one guess is significant, So here we've got 5 sig figs. So you guys are really going to have to practice with the zeros because they can get a little bit confusing, okay? So number 9, we've got 4.0 times 10 to the third. So if we were to write that in standard form, we'd go 1, 2, 3. So that would give us 4,000. And then we'd go, oh, well, that has one significant digit there because those 3 zeros are placeholders. But writing it as 4.0 times 10 to the third, it's specifically saying that the 4 and the first 0 right there, which correspond to those guys right there, are significant, okay? So that one would be certain, and that one would be uncertain. That's our one and only guess. And then these guys over here are just placeholders. So again, anything written in scientific notation is going to be significant. So look at the coefficient here. And what we would say is number 9 has 2 sig figs. Now number 10, when we look at it, we can see that the coefficient has just 1 sig fig. So there we go. Now if you want to write that out in standard form, the 3 with all the zeros on the end of it, feel free to do that, but we can see here that we only have 1 significant digit. Okay, so let's take a look at measuring this fish right here with 2 different rulers. So hopefully this will make it a little more clear. So we're measuring this fish, and the top ruler has less precision than the bottom ruler. And we can see that the top ruler is measuring by every 10 centimeters. So when we measure that, we're going to say, okay, it's 50 something. So I'm certain here. And then I need to make a guess. Now students don't like to make a guess, but you have to, okay? So the person who made this slide said, okay, my best guess is that there's a 3 in the ones column there. So that one is your guess. That one is uncertain. And here we have how many sig figs? 2 sig figs. Because all of our certain digits and our 1 uncertain digit on the end are significant. Now, if somebody else looked at that and said, no, 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 I think that it's 54 centimeters, would that be okay? Yes. If you're using the top ruler, that would be okay because the digit that's in this column right here is the guess. Okay, so what if we measure the fish with the bottom ruler? Well, you can see that with the bottom ruler, we are measuring every 1 centimeter. So if we look right here, we can see that we've got markings at 50, 51, 52, 53, 54, 55, etc. So if we look at the ruler, we can see, oh, okay, it's definitely 53 point something. It's not 52 and it's not 54. So I've got 53, and both of those numbers are certain. And then I need to make a guess. And you would say, okay, it's 53 point something, and my best guess is that it's 53.5 centimeters, and the last value is your guess. That's uncertain. And then it doesn't make any sense to report more numbers after this second 5 here because that 5 is already a guess. So any more would just not make any sense, okay? So this one right here has 3 significant figures. And because it has 3 sig figs and the measurement above has 2 sig figs, we can see that the measuring device used on the bottom right there is a more precise measuring device than the one on the top. Now, measuring liquid in a graduated cylinder. So this right here is a graduated cylinder, and it'll go all the way down to 0 on the bottom, and then it'll have a little base that goes around like that so it doesn't tip over. So when you're measuring water in a graduated cylinder, you want to look at the bottom of the meniscus. This thing right here is called a meniscus. You want to look at the bottom of the meniscus where that falls. The water is attracted to the glass, so it'll creep up the sides right there. So notice how we're measuring every 1 milliliter here. So we have 30, 31, 32, 33. So we are certain that we have 32 milliliters and not 31 or 33. And then we need to make a guess. So right here is 32. And then on here, this person has guessed that it's 32.0 and not 32.1 or 32.2. So this right here is uncertain, or that's our guess. Now, students don't like to do that, make the guess between the markings, but you are supposed to, because again, that's reporting the accuracy or the precision of your instrument. So that should be reported as 32.0 or 32.1 or 32.3, because N is a guess, and not just 32. Now, what happens if you are looking at a digital display? So say you have a balance and you put an object on your balance, and the balance reads out 2.014 grams. How many sig figs there? This is 4 significant figures. Now, the digit on the end, that is the scale or the balance's best guess, okay? So you wouldn't go ahead and try to give another digit after that, trying to guess. When you have a digital display, it's giving you its guess on the end. That's why the end number fluctuates sometimes. So maybe you have heavy air currents coming through the classroom because you're sitting next to a vent or something. That might fluctuate a little bit. So that's how that works with a digital display. All right, let's do a little more practicing here. So how would we report the measurement for this ball here, this metal ball? Well, the little tiny markings are our millimeters, and then the big markings, those are centimeters. So let's go with the centimeters. And then the millimeters are the tenths of a centimeter. So are we sure that this ball is measuring 2 centimeters and not 1 centimeter or 3 centimeters? Yes. So what we do is we say, okay, we've got 2 there and I'm certain. And then we're going to say point something, because this measuring device is measuring in tenths of a centimeter. So we've got 2.1, 2.2, 2.3, and right on the 2 is 2.0. And we can see that it's measuring 2.1 something, and it's not 2.0 something, and it's not 2.3 something, it's 2.1 something. So we are sure that it is at least 2 centimeters, and we are sure that it is at least 2.1 centimeters. So both of these right here we're certain of, and then we have to report one more digit because we need to make a guess on the end. So maybe you say, okay, that looks like it's 2.15 because it looks like it's right in between 2.1 and 2.2. And maybe I look at it and say, no, that's 2.14 centimeters. So who's correct? 2.14 or 2.15? We're both correct because this on the end is your guess. That's your uncertain digit, okay? So how many sig figs do we have here? We've got 3 sig figs here, 3 significant digits. So again, you guys, you got to make a guess, okay? Because you're reporting something about the precision or the accuracy of your measuring device when you report a certain number of significant digits. We could also do it in millimeters. Now, there are 10 millimeters per centimeter. So if you were to report it by millimeters, you'd have 10, oops, there we go, 10, and then 20, and then you would say, okay, I've got 21 right there, okay, 21 millimeters, and I'm not quite to 22 milliliters yet, so am I saying milliliters? Millimeters. This is 10 millimeters, and this is another 10 millimeters, and there we have 1 millimeter, and right here we have another 1 millimeter, so that would be 22 millimeters, but we don't have that yet. We have 21.5 millimeters, and 21.5 millimeters would still be 3 sig figs. Okay, so let's look at another graduated cylinder. And notice that we're measuring by every 1 milliliter here. Liter is a unit of volume. So here we have 51 and 52. And right here we've got 53. And then right here we've got 54. And then the big line is 55 milliliters. Okay, so we are definitely sure that we've got the 5 there, so that we don't have 40 milliliters and we don't have 60 milliliters. We've got 50 something. And now there's markings every 1 milliliter, so we definitely have to report that. And it's not 51, it's not 52, and it's not exactly 53 yet. It's a little bit under 53. So we have to go back to 52 point something. So we're sure that it's 52 point something, and it's not yet 53, and it's definitely not down at 51. And remember, you need to make your guess. So we're sure it's 52 something. So both of these right here are certain. And then we have our uncertain value. And that's our guess in there. And we have to read the bottom of the meniscus right there. So maybe you guess that it's 52.9. And maybe I say, no, I think it is 52.8 milliliters. Who's correct? We're both correct because the last value is uncertain, okay? So that's how that works. All right, so a little example of how this is important. So there was a team led by Sir George Everest in 1856 to measure the height of Mount Everest. And what happened is, using their surveying equipment, they found that they had exactly 29,000 feet. Now, the newer measurements are a little bit different, but this was back in 1856. They got exactly 29,000 feet. Now, they thought, oh no, if we report it as 29,000 feet, People reading this in the newspaper, because people got news from newspapers back then, will think that our measuring devices aren't very accurate. So how do we do this? Maybe we can report it in scientific notation so people know that we have 5 significant figures. But most people reading that would be like, what on earth is 2.9000 times 10 to the 4th? I don't get that. So what they decided to do is they decided to report it as 29,002 feet. And that makes people know that their measuring devices were a whole lot more accurate than if they could only get a measurement of 29,000 feet. So they lied just a little bit, so it looked like they had better instruments and were doing their jobs. So there's an example there. All right, now we need to go to calculation with significant digits. So the multiplication and division rules for significant digits are different than the addition and subtraction rules with significant digits. So more rules, yay! So the multiplication and division rules say that the final answer that you give has to have the same number of significant digits as the measurement that had the fewest significant digits. So what we have to do is go through every measurement and identify the number of significant digits. Then we have to do the calculation, and then we have to decide how many significant digits we have in our answer. So the significant digits for 22.2, how many do we have there? That is 3 significant figures there. What about for 3.4654? That's going to be 5 significant figures. So the rules say that the answer is going to have the same number of significant digits as your measurement that had the fewest sig figs. And the fewest sig figs here is 3. 3 is smaller than 5. So you'd go ahead and you'd do this calculation, and you would get something like 76.93, and then centimeter times centimeter is centimeter squared. You don't want to forget your unit because you want all your points. And then you go, okay, I need to report the final answer with only 3 sig figs because that's the rule, okay? So you start with the digit on the left. So there's 1 sig fig, 2 sig figs, 3 sig figs, okay? So we're gonna stop in the tenths column. The 9 is in the tenths column when we give our final answer, but we needed this digit right here to tell us whether we were gonna round up or just stay at 9. Now, if it's 5 or up, go ahead and round the next digit up, but if it's below 5, you're gonna go ahead and keep the next digit as is. So we would report this answer as 76.9 centimeters squared, and our final answer has 3 sig figs, and that is the same as the measurement with the fewest sig figs there. Okay, so that's how that works. Now, example number 2, we have 0.0009 millimeters divided by 0.340 millimeters. So right here, we have how many significant digits? We have 1 sig fig there. Only the 9 is significant. These zeros up here are placeholders, because if you didn't write the zeros up there, you would have 0.9, and 0.9 is completely different from 0.0009. And 0.340, how many significant digits there? We've got 3. The 0 on the front is a placeholder. This 0 all the way to the right, that's a trailing 0. That is significant. It's telling us that we're sure that that 4 is a 4 and not a 3 or a 5, but we are uncertain about this spot. So that 0 all the way to the right could be a 0 or a 1 or a 2. We're uncertain there. So there we have 3 sig figs. So if we did this calculation, what we would see is that the millimeters would cancel out, because anything divided by itself is what is 1. So 3 divided by 3 is 1, 12 divided by 12 is 1, car divided by car is what? 1, millimeters divided by millimeters is 1. So this is one of those answers where you won't have a unit. So you would do the calculation with your calculator and you would get 0.00265, and then you would say, okay, my answer needs to have only the same number of significant digits as the measurement with the fewest sig figs, which is right there. 1 sig fig on that value, on that measurement. And you start with the first significant digit that you see all the way to the left. So we know that we're going to end our final answer right there in that column where the 2 is. And we need the number next to it to tell us whether we're going to round the 2 up or leave it as a 2. And 6 tells us that we're going to round the 2 up to a 3. So our final answer is 0.003. Okay. Again, you guys, if I've made some kind of calculation error somewhere, like you're following along with your calculator and you're not getting the same values that I'm getting, please shoot me an email and let me know. Occasionally I type in things wrong to the calculator, and that's okay, okay? All right, just let me know. So the addition and subtraction rules are different from the multiplication and division rules. Addition and subtraction rules say that the final answer is written so that it has the same number of decimal places as the measurement having the fewest decimal places. What on earth did I just say? Well, this is what you're going to do. So look at example 1. So here we've got 3 sig figs, here we've got 5 sig figs, and here we've got 1 significant digit. But that doesn't really matter because we're looking at our measurement values and looking for the one that is reported to the fewest decimal places. So let's go ahead and line up our decimals like we were taught to do in elementary school and middle school, and we all thought, why do I have to do this? I'm never going to use this. Now, ha 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 ha, that's coming back to haunt you right now. And then we have five zeros after the decimal for that one. And we're going to add these up. So what we're going to do is we're going to bring down our decimal to right here. And 44.4, that value only goes to the tenths column. So remember that here we have the ones and there we have the tens, but behind the decimal it starts with tenths. You don't have any oneths column, starting with the tenths column, okay? So 44.4 only goes to the tenths column, so your final answer needs to end in the tenths column, so I go ahead and put a box around it. So go ahead and do that, and that will tell you where you're supposed to stop for your final answer. Now, if we add this up, we are going to get 46.7966702. Okay, so right there, the box is telling you that your final answer needs to stop in the column, in the tenths column, where the 7 is. But we need the 9 over here to tell us whether we're going to round the 7 up or not. Now, do we? Yes, we do. So our final answer is 46.8. And we have liters plus liters plus liters. You want to make sure all of your units are exactly the same when you're adding things. You can't do milliliters plus liters plus kilogram. You have to have the same units. So this is 46.8 liters. So these rules are different from multiplication and division. So make sure you're very familiar with these. So example number 2 says we've got 4,107 minus 608.7. And we can see that 4,107 ends in the ones column. So we're going to go ahead and put a box around the ones column so we know where to end our answer. So if we bring the decimal down right here and we do the subtraction, we're going to end up with 3,498.3. And right there we can see the boxes around that 8. So we're going to go ahead and report this value as 3,498 inches. We didn't round the 8 up to 9 because the 3 told us we didn't have to. And you have inches minus inches, and of course that's inches. Okay, so let's practice some. Yay! So we have 200 times 3.44 times 9.30, and 200. We've got one significant figure there. Those zeros are placeholders. 3.44 is how many? That's 3 significant figures. And 9.30, how many sig figs? We have 3 sig figs here. We've got a 0 all the way to the right in a decimal number. So that 0 in 9.30 is not a placeholder. That's telling you that your measuring device is better than a measuring device that measured something at just 9.3. Okay? So we do this multiplication, and what we will get for the answer is 6,398.4. Now we have 1 sig fig, 3 sig figs, and 3 sig figs for a measurement, so our final answer is only going to have how many significant digits? Only 1. And we start from the left, and here's our first sig fig there. And then we look at the 3 to tell us whether we're going to round that 6 up to a 7 or not. That's a no. So our final answer is 6,000. That has 1 significant digit, and those 3 zeros are placeholders. Okay? So it seems really weird to students to get rid of numbers, but if you want to report that as 1 significant digit, that's how you have to do it, okay? So that 6, that's your guess. So reporting any non-zero digits after that doesn't make any sense. We're not even sure that it's 6,000. It might be 5,000 or 7,000, but that's what we got there, okay? All right. So number 2, we've got 3 significant figures because the zeros up at the front are placeholders, divided by 2 significant figures. So you do 0.00309 divided by 4.4 times 10 to the third. At that point, I would hit equals. And then I'd say times 999, which is 3 significant figures. So what we'll get for the answer there is 0.000701557. Now we've got 3 sig figs, 2 sig figs, and 3 sig figs. So our final answer is going to have how many significant digits? 2. So we go to the first number that we see there, our non-zero digit there is 7. So 2 significant digits there, and then we're going to look at the 1 to tell us whether we round the 0 up or not, and that's a no. So our final answer is 0.00070. Those first 4 zeros are placeholders, and the 0 all the way to the right is a trailing 0 in a decimal number. It is significant. Okay, number 3, what we have is 24.464 minus 2.2. So we are going to use our addition and subtraction rules here. So we've got the box here, bring down the decimal point to here. And what we will get when we do the subtraction here is 22.264. And because we put the box around the tenths column, we know that we need to end there. We have the 6 here to tell us whether we round this 2 up or not. Do we? Yes, we do. 6 is above 5. So our final answer would be 22.3. And we're finishing in the tenths column because 2.2 only goes over to the tenths column. And that's what the rules say for addition and subtraction with the correct number of sig figs. Okay, so number 4, what we have is 0.000800 plus 909 plus 3.6. So if we line up all the decimals here, and the decimal point for 909 is right there, it's gonna be brought down to here. And 909, that only goes to the ones column. So our answer can only go to the ones column. Now, if we do all of the addition on this one, what we'll get is 0.00800. Okay, so this is here, 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 and then we add the 0 and the 6. So we get 6 there, and then 9 plus 3 is 12. Carry the 1, and then we've got the 1 down there. And we've got 912.600800. And what we need to do is we need to finish this in the ones column. So we look over at the 6 right here to tell us whether we are rounding up or not, and we do. So we report this answer as 913. Okay, so if we kind of think about this in real life terms, why we're doing this, what we can say is, okay, say you have $909. If someone gives you $3.60, that's like, okay, that's cool, man. That means something, right? You can add your $3.60 to your $909, and you got about $913, right? Recalling that the last digit has wiggle room on it. That's an estimate there. So you have about $913. But what if someone gives you $0.000800? So that's way less than a penny. Does that mean anything to you? No, because what does that do for you? And you can see that reflected in our addition down here. The .000800, that didn't even register in our final answer. Okay, so that is kind of a relation to an everyday real situation. Alrighty, so accuracy and precision. So I've been talking about accuracy and precision a lot in terms of measuring devices and kind of using them interchangeably, but there is a slight difference between them. So precision is how well several determinations of the same measurement are agreeing. And so this is reproducibility or repeatability. And accuracy is agreement of a measurement with an accepted value. So say that you know that you weigh 119 pounds and you get on the scale and it says 119 pounds, and you step off and you step back on and it says 119.5. You step off and you step back on and it says 118.5, and you step off and you step back on and it says 119, and you step off and you step back on and it says 120. Your scale is pretty precise because it's giving you the same measurement basically over and over again. Now if you stepped on the scale and it said 119, and then you stepped off and you stepped back on and it said 125, you stepped off and you stepped back on and it said 119 again, and you stepped off and stepped back on and it said 123, that would be low precision because it's not giving you the same measurement over and over again. So that would be a measuring device with low precision. Now, accuracy is the agreement of a measurement with an accepted value. So say you go to the store with the bionic scales and they measure you to be exactly 119.00000 pounds, okay? And you step on your scale and it says 119.0 pounds. Well, if you keep doing that and it keeps giving you 119, you go, okay, my scale's pretty accurate. And it's pretty precise if it keeps giving you 119.0. But if you step on your scale and it gives you 132 pounds, well, then you know that your scale is not very accurate. It's off. It's not agreeing with the true value. You can get a measuring device that has low accuracy but high precision. Meaning, what if your scale is just off by 10 pounds? And every time you step on it, it tells you you weigh 129.0 pounds. Well, it can be very precise if it gives you a value of 129.0 like 11 times, but it can still not be accurate, okay? So that's a little bit of difference between accuracy and precision. But in real life, we tend to use the terms interchangeably. All right, so the dartboard below, it's showing you the difference between accuracy and precision, and high and low accuracy, and high and low precision. So with a dartboard, what you want to do is you want to hit the center circle, the bullseye, with your darts. So in example A, all three of your darts are hitting the bullseye, so you're very accurate, and those hits are very close, so you also have high precision. In B, your hits are in the bullseye, but your hits are a little bit far apart from each other. So we have high accuracy but low precision there. Now in C, you're getting all of your hits in the same region, so you've got high precision there, but you have low accuracy because you're supposed to get them in the bullseye right here. Okay, so the accuracy is off, but your precision's high. And D, you've got low accuracy and low precision, so you're just all over the place. You're not getting where you're supposed to be, and your hits are not in the same spot. So let's do one problem here for accuracy and precision. So we've got 4 students, A, B, C, and D, and we want to determine whether they have high or low accuracy and high or low precision. So student A takes exam 1 and gets a 99%, and takes exam 2 and gets 100%. So do we have high or low accuracy there? We've got high accuracy. So the 100% is the most accurate, very high accuracy. Now, are those two scores really close? Yeah, so we have high precision here. Now, student B gets 100% on exam 1 and 89% on exam 2. So the accuracy, is it pretty high? Yeah, the accuracy is still pretty high, and 89% is still really good. That is pretty close to 100% compared to what student D is getting. Okay, but what about the precision? Well, the precision is a little bit lower if we're looking at student B versus student A, so we'll give that a low precision there. The two scores are not close to each other. Student C, how about the accuracy there? Low accuracy, but what about the precision? super high precision there. So student C can go home and say, Mom, I have really high precision in my chemistry grades. Woohoo! Okay? Doesn't mean they're very accurate though. And student D, what about the accuracy? Low accuracy and the precision? Low precision also. Those two values are quite far apart. Okay, so that's the end of this lecture. I will see you in the next lecture. And that's it. Bye-bye.